Howdy, this is Team 5 of MXET 375 presenting our final project, the Robot Walker. My name is Adrian Montero. I work with the team to contribute to the project as a whole, and I work mainly on 3D printing and Simulink modeling.
Howdy, my name is Guillermo Rivera. Of course, I helped my teammates with all aspects of the project. However, I mostly focused on the electrical and coding portion.
Howdy, my name is Juan Lara and I assisted with every category of this project but mainly focused on the electrical and presentation slides. Due to the difficulties encountered in the 3D modeling process, the new goal of the walker was to observe and examine the range in the motion and observe how different values such as voltage, current, and revolution per minute (RPM) are affected by such movement. By this, we will analyze the stated parameters that will be displayed and compare them with the results of the Simulink simulation.
For the coding aspect of the project, the team downloaded the Arduino software and installed the library functions necessary in order to properly connect to the INA260. The code was made to be able to control the speed of the motor as well as for how long it should spin, all while recording the desired parameters such as voltage, current, and motor RPMs. More specifically, it made the motor spin for 10 seconds and recorded the data at 10 millisecond intervals. Other than the physical components, a challenge arose when trying to convert the data to serial monitor to a CSV, but after installing software called PuTTY, the measurements were able to be analyzed and plotted correctly in Excel.
In summary, the most important pins utilized in the Arduino in order to make the motor work were the D2, A0, D3, A4, A5, and BN, which is the output of the Arduino, which was connected to the INA260, providing a voltage to the motor.
Here's an image of the completed circuit. At first, we were unable to power the motor with the charge from the 9-volt battery. However, after configuring the correct V pin to the INA260, it worked like a charm alongside the code commanding it.
The designing and printing process was the task that took the longest to complete. Designing the robot mostly comprised of working on getting the motion to move smoothly in the CAD design. The design process took roughly around 2 weeks to finalize. On the first revision of the model, the 3D print came out too tight, so the model had to be adjusted with larger spacings. The second revision came out better, but it still had some issues with the print itself. In order to get all the pieces to fit correctly all together, all of the parts had to be hand sanded and even drilled to the point to where the parts would fit smoothly together.
Initially, we made the block design by hand, but since it took too long, the team decided to research how to import a SolidWorks assembly into Simulink. This was done by importing an extension into MATLAB to read and exported SolidWorks assembly file. This efficient method streamlined the process of creating a mathematical model in Simulink directly from SolidWorks.
After importing the model into Simulink, the only features added to the block diagram were scopes and the electromechanical subsystem. Next, we adjusted the dampening coefficients to something small, then ran the simulation. You can see in the video that the leg is moving as expected.
Even though the simulated experiment used a slightly different coefficient of friction, the results from the real-life and simulated plots were thankfully very similar in shape. As for the voltage of the motor, it started higher as it was the initial flux and then settled down very closely to 4.7 volts. The current, of course, initially rose from 0, then fluctuated between 0.25 amps to 55. The RPM also rose and ranged from 800 up to 1400.
Throughout the process, the team experienced issues such as the electronic wiring, since they kept breaking, making us change the damaged wires again. Also, the plans the team initially had were unable to happen since when 3D printing the parts were not coming out as requested, making it hard for the whole body to be built. Lastly, the coding was another tough issue to fix since the motor would not rotate nor know that data was being collected. Fortunately, the issues were fixed and the team was able to perform their project successfully and obtain what they were looking for. As the team expected, the results of both the walker and the Simulink simulation outputs were pretty similar, demonstrating how simulated systems are accurate to those of the real world.
This concludes our MXET 375 project. Thanks and gigum.